we have two different z-tables, and they are used a bit differently. So let's get into it. So we have this first version of the z-table, and we have this second version of the z-table. So let's start with the first one. As you see here, you have the area underneath the graph truncated by this vertical line at this number z is a probability. And this z function is a probability function because if you take the whole area around here, then it sums up to 1, which is equal to 100%, right? But we are interested in finding the tail probability, which means that we have this number, this z number, which often comes from your coefficient value, if I can write that correctly, divided by the standard error of the coefficient. Is it possible? Okay, coefficient. Okay, so this is your z number, which is often called the t-stat. Okay, and the reason why the reason why it's called the z is that if you have a lot of data, like 400 or more data, then the t-distribution resembles the z-distribution, which is the normal distribution, right? Okay, so what we are interested in is to find the tail probability of a certain z number. But before we get into the hypothesis testing of it, we can just get the probability of this tail and how to use the z-table. And the main idea behind this first version of the z-table is that if you have a number, the z, for example here, and this number is negative 2.90, then you can just go here in the z column, right? And you can find negative 2.9, which is here, and the decimal here, the second decimal here is 0, so you get this column, okay? So now you have the p-value corresponding to a z number of negative 2.90, which is 0.0019, which is equivalent to 0.19%. Okay, so this area here is 0.0019, which is equal to 0.19%. Okay, so this is how you find the tail probability of or corresponding to a a z number of negative 2.90 standard errors away from the mean, which is 0. And if we have a different example here, we can just change our example. And if we have a different number, then for example, negative 1.44, negative 1.44, then this number is maybe around here, right? And what is the tail probability here? Now we have to go to this column, the Z column, find the corresponding to first digit, which is here, negative 1.4, and the third digit is 4. Let's see, 4, and then you just find this number, which is 0.0749, which means that the probability, the area here, is 0.079, which is we have more digits here, 49, which is equal to 7.49%. Okay, so this is how you find the tail probability from this Z table if you have the Z statistic. Okay. One important thing to mention is that if you draw a line here in the middle at 0, the left side is a reflection of the right side. So this distribution is symmetrical around the mean, which means that if you have a number of negative 1.44 on the plus side here, right? So if you have a 1.44 and you would like to find the probability in the positive tail, then you could just find the left tail here, the left tail probability, and just to remove some clutter, and you could use the negative of the 1.44 to find the left probability, because then you have found at the same time the right tail probability of the positive number of this. So this is 0.0749, which is equal to 7.49%. So whenever you find the left tail of this number, you find at the same time the right tail of the number, the Z number, with the opposite sign. Okay? Now that we have removed the clutter here, we can look at how to use this table in hypothesis testing. So let's see here, we might start with a two-sided hypothesis test. Okay, so in this case, you are wondering if your coefficient is different from 0. And this is your alternative hypothesis. So I like to start with the alternative hypothesis because this is what you are going to, this is what you're actually testing. But statistically, it's easier to test the opposite and prove this wrong. So if this alternative hypothesis is correct, it's the same as saying that the null hypothesis is false, right? So you are wondering, can we prove this null hypothesis wrong in order to show that the alternative hypothesis is kept? Well, what you're doing here is you're looking at the difference between beta and a number 0, right? So, and in this case, you are interested in whether or not this beta is different from 0 in either direction, positive or negative. So let's say that you have this, you've gotten this estimate of beta, we call it beta hat, and this is from your regression, and you have this distribution around this estimate, and this comes about because you have a certain variation in your estimate, and we call this, or we measure it by the standard error of the beta hat. So this creates this distribution, and the way you calculate how far away your null hypothesis is from your estimate is by the t-stat. And the t-stat is just the coefficient divided by the standard error of this coefficient, right? So this can be, this beta can be a slope from your regression model. And if you have a lot of data, then this t distribution is equal to the normal distribution, and this would be your z number. Okay, so how can we use this? Well, we can how can we say this? We can just check how far away from our estimate is our null hypothesis value. And if our null hypothesis value falls into one of these tails here or here, because we have a two-sided test, then we are led to believe that if the null hypothesis value is here or here, then we are led to believe that, well, this is not very probable, so we reject the null hypothesis and instead keep the alternative hypothesis of these numbers being disequal, okay, or unequal. So the way we can use the z-table is to find the tail probability of getting a number further away from the null hypothesis than our beta hat. I think it's better to show by example. So let's say that our z was negative 0.14, and we can go to our table and we can see that if we have a number here of negative 0.14, it's quite close to the null hypothesis, right? And if we have this number, we have to find the probability here. Okay, so if we go to this z column, and our two first digits would be negative 0.1, so negative 0.1, and the third digit is 4, so we have negative 0.14, and we find that the probability is 0.4443, so we have 0.4443 here, which is 44.43%. And this tells us that if our standard error from this coefficient is correct, then in 44.43% of the random cases, we would get a z number less than what we got. Okay? But remember that we have a two-sided test, right? And the way we can find the right tail here, the probability in the right tail, is to use the symmetry, right? We know that this 44.43% probability is the same as if we just go to the right with plus 0.14 and find the tail probability. So this probability is also 0.4443, and this is 44.43%. Okay, so if you would like to have the probability of getting a z value of more than plus 0.14 and less than 0.14 negative, then you just add up these two probabilities, which is equal to 0.8886, right? Which is 2 times 0.4443. And this is because we have a two-sided test. And the reason why we don't find this plus 0.14 in the table, plus 0.14 would be over here, 0.1 plus the third digit, 4, would be here, is because this 0.5557, it's really the, if we take away this clutter, if we have the 0.14 here, and this is the intersection of these columns and rows, and we have this is actually the tail probability, the left probability of this z number. And then you would get, you would contain the null hypothesis, right? So what you were interested in for the two-sided hypothesis test was how far away to either side you had to go and find the tail probabilities, right? So the way you use this version 1 of the z-table is you would like to find the tail probability. Okay, so you have the z number, the t statistic, and you would like to find the tail probability. So you have a lot of information here, a lot of probabilities, but for the second version of the table, you have also the left tail probability. So, and remember that you have the z number, but this is testing the negative of the z number. And so if you have a z number of around negative 0.14 here, then you can go here, but you wouldn't find exactly that number. It would be in the middle here somewhere, and you would find that the probability is between these numbers. Okay, so the previous version of the z table is more fine grid and more detailed, but this this table is often used in the way that you first decide on a probability. For example, the one-sided probability should be 0.05, and then you go down here to 0.05 here, and you find how many standard errors away from 0 you have to go to have a tail probability of 0.05. And if you would like to have a two-sided test, you could go to this column where you have the plus or minus z should be greater than your critical value. And in this case, you would like to have 0.05 here, you would like to have 0.05 here, which means that you have a significance level of 10%, and coincidentally you have that down here, right, which corresponds to the tail probability of 5%, because you have 5% in one tail and 5% in the other. So this is how you use this second version of this model. It's quite practical to find the critical value corresponding to a often used significance level. So for example, if your two-sided test had a significance level of 5%, which means that, well, you accept a 0.025 probability in one tail and 0.025, it should be 0.25, which means the significance level is 0.05, which is 5%. Then you go down here and you find the probability, the total probability of these two tail probabilities, and you have the often used critical value of 1.96, which means that if your estimate is more than 1.96 standard errors away from the null hypothesis, you are led to reject the null hypothesis because it's not very likely to be true, and you keep the alternative hypothesis. And the way you find whether or not this estimate is closer than 1.96 standard errors away from the null hypothesis is just to calculate the t-stat, which is the coefficient divided by the standard error of the coefficient, and this is the t-stat, and this is the number of standard errors away from the null hypothesis that your coefficient is. So in this case, if the coefficient is above 1.96 plus or minus, then in absolute value, then you are led to believe that the null hypothesis is not true.